Good morning, everybody. Just getting things prepped here. Turns out that the update that's going on for my Inkodo, which is the digital whiteboard that I use, is taking a lot longer than I wanted it to. So this will give me a moment to talk about the grading of your exams and all that. So I'm still grading exams. You'll know that your exam is graded if you log in to My Open Math and go to the grade book, and there's feedback on your exam, and the final feedback says graded. That just tells you and me that I've finished grading your exams. So that's a little heads up for you. The other thing is, remember, next week starts spring break, so we will not have classes next week. And you should be working on section 11.1. Anything else I need to make mention there? I don't think so. And I'll go ahead and share my screen. You're going to see on my screen right now, it's still importing my lecture. So, but that's perfectly fine. Open here, share screen. And where is my Inkodo? There it is. Share. There we go. So it's still importing. Takes just a few more moments here, and then we'll jump right into it. As you recall, you might not recall, but on Wednesday of last week, we were just starting into section 11.2, which is series, which is basically the theme of the rest of this chapter. It's all about series. There we go. We're all completely loaded in. I have two of the first pages, so let me go ahead and delete this one right here. And yep. All right. So where we left off, which was really at the beginning of it, is this definition right here. Let me get this large-ish. And that's definition of convergent and divergent series. It is assumed that you watched all of the videos on series as the reviews videos, that I have posted in the announcements area. Yeah, so and those weren't done in class. Those were just done for my pre-calculus students. So just a heads up that is something that you might want to view if it's been a while since you've had series, which probably has been. And then I mentioned last class in this very zoomed in ink here that every sequence that you're handed actually is two sequences, and that's going to be critical to understand. So even though there is a video online or a set of videos on how to on a review for series from pre-calculus, I still like to mention a few things here and there. And this is one of those, that every time you're handed a sequence from this point forward, you need to understand that sequence actually is two sequences. One being the base sequence itself. For example, in this case that I wrote last Wednesday, a sub n is defined to be 1/2 to the n minus first power, which is 1/2 to the n minus first. And when you want to write out the terms of that sequence, well, when n is 1, you get 1/2 to the 0th, or 1. When n is 2, you get 1/2 to the first, which is 1/2. And when n is 3, you get 1/2 to the 3 minus 1, which is 2, which is 1/4, and so on and so forth down the line. However, then we can create a sequence of partial sums, which just basically means we can add up the first n terms and build a sequence based upon that. For example, and I should mention this, that our sequence is, let me get my highlighter out. I think this is a highlighter. Yes, it is. Okay. So our sequence is, our new sequence is S sub 1, S sub 2, S sub 3, S sub 4, S sub 5, and so on and so forth down the line. And how those are defined as being the sum of the first n terms of the base sequence. So, for example, S sub 1 is the sum of the first term of the base sequence. So it's just A1. S sub 2 is the sum of the first two terms, which would be 1A1 plus A2, which is 1 plus 1/2, which tends to be 3/2. S sub 3 is the sum of the first three terms of the sequence, A1, A2, and A3. And if you take a look at it, it's actually easier to write. Yeah, I know S sub 3 is A1 plus A2 plus A3, but it's easier to note that actually it's the sum of the first two terms, which we just computed. So it's just easier to write it that way. That's the sum of the first two terms plus the next term in line. That way we don't have to add up three terms, we just add two. And you define all the partial sums that way. All right. And so in general, in summation notation, S sub n here is just going to be the sum of the first n terms. That's what the summation is, of sum of the first n terms of our base sequence. That's what S sub n is. And this gives us, if we were to write that, and let me get a black pen going on here. And I haven't tested my pen this morning, so we'll find out. This will build us a sequence. Oh, that's very large. Let me go ahead and I wonder if this is going to be just as massive. No, okay. That builds us a sequence S sub 1, S sub 2, S sub 3, and so on and so forth down the line, all the way to S sub n or S sub infinity, right? As n goes to infinity. It builds us a brand new sequence, and we can determine based upon 11.1 whether or not that brand new sequence, I'll call this the sequence of partial sums, we want to know whether or not that brand new sequence of partial sums converges. And we take the limit as n goes to infinity of this sequence S sub n to determine whether or not that sequence of partial sums converges. So I'm spending a lot of time on just this part of the discussion because it's so critical to understand, to create that level of distinction between the base sequence and the sequence of partial sums. And again, we would like to know what that limit as n goes to infinity of that sequence of partial sums is, if it's finite. Very often it's going to not be finite. So an example of a sequence of partial sums that's not finite, where the base sequence is finite, would be something like this. Let's pretend as though, as an example, we have a sub n, which is defined to be 1, always. So if you were to write out the terms of your base sequence, it'd be 1, 1, and 1, and so on and so forth down the line. That sequence totally converges, right? So note the limit as n tends to infinity of a sub n. Well, since a sub n is always 1, that's the limit as n tends to infinity of 1, which is just 1. Not a big deal. The base sequence totally converges. So I'm going to write that down. This implies that the base sequence a sub n converges to 1. There we go. But then you could start talking about the sequence of partial sums. That I don't need a definition for because I'm using the base sequence to build it. So for example, S sub 1 is just the sum of the first term of our base sequence, which is 1. S sub 2 is the sum of the first two terms of our sequence, which is 1 plus 1. And S sub 3 is the sum of the first three terms. And you probably would get bored if I continued with that. So I'll just go ahead and say that's going to be 3. But you know the pattern, right? Dot, dot, dot. So S sub n is just going to be n. And note, in this case, while the sequence itself, the base sequence, converges to 1, the sequence of partial sums does not converge at all. The limit as n goes to infinity of S sub n, well, that's going to be infinite. In other words, these, I should put the implication signs there, implies the sequence of partial sums diverges. Well, I hope solidifies the idea of the difference between the base sequence and the sequence of partial sums. You can have a base sequence that converges, but a sequence of partial sums, as you can see here, that diverges. You can have a base sequence that converges. This base sequence right here will converge to 0. And its sequence of partial sums will actually also converge. So it could go both, or not both ways, but you could have a base sequence that converges where its sequence of partial sums converges or diverges. Just to let you know, if you have a base sequence that doesn't converge, the sequence of partial sums will not converge. That's kind of a theorem we'll talk about in the future. All right, there's a lot more theory behind the scenes that you should know for series, but this right here is pretty much the kicker. This is like what we need to start with. All right, so let's jump into an example. Find the first few partial sums, graph the sequence and the partial sums, and then ask or answer, does it appear to converge or diverge? If it converges or appears to converge, find its sum. If it's divergent, explain why. So what I'm going to do is on my desktop here, I'm just going to actually, I think what I'm going to do is search for Desmos sequences. And then I will showcase that to you once we get there. All right, so find the first few partial sums of this. Well, that just means, remember, this is, if it converges, this is going to be, and look how small my pen is here. Very, very small, right? But if that converges, it's just some value of S. And I think what I'm going to do is, can I make this oh, I can. There we go. All right. So if it converges, it'll just be some number. If it doesn't converge, then I probably would just say it's just divergent. I wouldn't call it S at all. I would just say it diverges. But let's, for now, suppose that it converges to some number S. To find the partial sums, I'll start with what's S sub 1. In other words, what if I add up only one term in this summation? So if I don't go from 1 to infinity, but instead start at 1 and end at 1. Okay, so let's go ahead and find out what S sub 1 is. And I'm going to actually zoom in down below here. S sub 1 is just going to be, zooming out, I'll just let these ends right here be 1. That's it. Nothing big. So that'll be e to the first minus, zooming back out, e to the 1 over 2. Okay, and I'm not going to do anything like simplify that. This is something that you need to know as you move forward in, especially in this course, but into differential equations as well. The idea of simplification starts to be shed a little bit. To find patterns in mathematics, you generally don't want to simplify. You want to leave things kind of unsimplified so you can see a pattern as time goes on. And there is actually a pattern to this summation. So let's go ahead and see what S sub 2 is. Remember, that means add the first term in this summation to the second term in this summation. So the first term we have actually down below, it's e to the first minus e to the 1/2 plus, actually I'll use a different color for the second term just so that we can really see the difference between the two. So I'll do it right here, plus, and then the second term when n is equal to 2, well, if that n is now equal to 2 and that n right there is now equal to 2, we have e to the 1/2 minus e to the 1/3. Let's go ahead and write that down. Plus e to the 1/2 minus e to the 1/3. Now you should see something happen in the middle. Those two terms in the middle, e to negative 1, or sorry, negative e to the 1/2 and positive e to the 1/2, those will cancel. I'm not going to cross them out yet, but I will once we get there. once we get to needing that information. Let's go ahead and just add up or find out what S sub 3 is, which is the sum of the first, second, and third terms of this expansion of the summation here. So again, n equals 1. Start there. That's e to the first minus e to the 1/2. Notice I haven't simplified anything. And then n equals 2. We have plus e to the 1/2 minus e to the 1/3. And then n equals 3. I'll use a different color for that. Plus e to the 1/3 minus e to the 1/4. That's for n equals 3. And now what I'm going to do is now I will go ahead and cancel out, just to showcase the idea, I'm going to cancel interior terms. That is, in the second sum here, I'll cancel these two. In the third sum, notice these two cancel as well as these two at the very end. Not the very end, but the second and third to last terms. So notice in S sub 2 and S sub 3, they have the same exact structure. They have e to the first, and then they have minus e to the 1 over something. The over something is kind of critical here. Let me see if I can maybe use a pen to showcase this. I'm not even sure if this is, oh, that's a terrible pen. I'll just point and arrow at it. I have to fix my pens after an update they did to this program. Anyway, notice that the last term for S sub 2 is e to the negative e to the 1 over 3, which is 1 more than 2. And notice the last term in S sub 3 is negative e to the 1 over 4, which is 1 more than 3. So in general, it's probably safe to say, although not a proof, but actually nobody would ask you technically to prove this, they would want you to find the pattern and then state the pattern, that the nth partial sum is going to be e to the first minus e to the 1 over n plus 1. Again, this is a great series to look at. This is called a telescoping series because terms cancel. So I'm going to actually write that in. It's a telescoping series because as you open up the series to see the partial sums, it collapses like a telescope, like an old pirate's telescope. It collapses to be just the first and last term of the series. So, all right, we've done that. Now let's read the instructions again. Find the first few partial sums. We've done that. Graph the sequence and the partial sums. Okay, so this is what I really want to do. I want to get us to see what a graph of the sequence and the first few partial sums look like and how we can do that. So I'm going to go to my desktop here and I'm going to share this Desmos. There we go. I'll share this screen right here. All I did was type in Desmos sequences, and you can open up one of those. I think the very first one. Nope, it's not the very first one because this one has sequence values. You can see here there's a sequence of values, but it doesn't have a secondary sequence. I don't see a second set of dots. So it must be this second one right here, or maybe the one that says sequences in series. Let's try that. Yep, that's it. Okay, notice that I have a sequence of purple dots here. I'll zoom in so you can see they are purple dots. But I also have a sequence of red dots. And those red dots are actually the sum of those purple dots. Notice those red dots blow up. So let's go ahead and take this person's sequences in series Desmos applet and let's change it up a little bit. Describing to you what each of these means. They're defining a set of points. The set of points goes 1 all the way to some stopping number that we can decide because that stopping number is little n, and that's right here. So if you want to change that to be 1,000 or 50 or whatever, you can totally do that. So this notation here, bracket 1 comma dot 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 comma little n, just creates in Desmos a sequence of integers 1 through n, and then we can define what that ending point is later on just by saying, oh, by the way, it stops at 100. You can change that to whatever you want. The sequence that we want to deal with in our case is e to the 1 over n minus e to the 1 over n plus 1. Notice the n here is going to be a capital. So I'm going to go ahead and type that in. E raised to the 1 over n minus e raised to the 1 over n minus, no, plus 1. Okay. And then, so that's our sequence, our base sequence. I'm not 100% sure what this a is, so I'm going to ignore that for now. And then plots the sequence. So purple points are n, comma, a sub n. Remember, our sequence, not our series, but our sequence that we're going to be adding up is e to the 1 over n minus e to the 1 over n plus 1. And so that's what we define to be a sub n. And so that's exactly what these purple points, I'm going to turn off the reds. That's what these purple points right here are. So like this right here is a sub 1. It's e to the first minus e to the 1 over 2. And there's a sub 2. It's e to the second minus e to the 1, or I'm sorry, e to the 1 over 2 minus e to the 1 over 3. And this is the next one. This is e to the 1 over 3 minus e to the 1 over 4, and so on and so forth down the line. But that's not what they asked us. I mean, they did ask us to plot out the sequence itself. You can see the sequence tends to go to collapse to 0 pretty quickly. You can zoom in if you want and see that. But they also asked us to graph the sequence of partial sums. And this is where it gets a little tricky. Luckily, if you just search for Desmos sequences in series, somebody has this already set up for us. So plots the sequence of partial sums. The sequence of partial sums, it's just going to plot at point, let's say 1, the summation 1 to 1 of a sub n. It says of k. You can ignore the of k. I think the of k is something I have no clue. Oh, of k. Yeah. This is just the k value. That's all. The kth value of a sub n. That's what it's plotting. Don't worry about that. Anyhow, it's plotting the sum of the first capital N terms of our series. So let me go ahead and turn it on and I'll describe it. In red, at n equals 1, it's added up the first term of our series. That's e to the first minus e to the 1/2. At n equals 2, it's added up that previous term plus e to the 1/2 minus e to the 1/3. And then in the next one, it's plotting the sum of these two terms right here. Actually, the sum of the first two terms. So I should say the sum of these two terms right here plus the next one in line, the third term. And that sum ends up being this. The fourth term would sum up 1, 2, 3, and 4. Actually, that is the fourth, isn't it? 1, 2, 3, and 4. So the fourth term would add up those 4, and it would be, is this the fourth? No, it's this one right here. Okay, that would be this guy right here. So it just continually adds up. Notice that it continually adds, and it looks as though it's converging to some height. In other words, it's sort of like, no, not sort of, it's exactly like what we talked about last week, which is that with the sequence, it's convergent if it tends to a value as n goes to infinity. And this looks like as n gets pretty huge, that this is tending to some value between 1.5 and 2. And we can actually find that value. Let me go back to my laptop here. We can find that value just by looking at our work that we did. And to do that, I'll tab again, share. Yes. Go to, yep. To do that, we're going to look back at our work, which again, I have to apologize. My ink is really weird here, but we know that the nth summation of our series is going to be e to the first minus e to the 1 over n plus 1. Now, if you let n go to infinity, so I'm going to go ahead and write that in here. Yes, I do. So the limit as n tends to infinity of s sub n, it looks like it's going to be the limit as n tends to infinity of s sub n, which is e to the first minus e to the 1 over n plus 1. Now, as n goes to infinity, we know from Calc 1 that, I'll use green actually, this exponent will tend to 0. And so we have e to the first minus e to the 0th is what this is going to tend to. Go ahead and use black ink for that again. And e to the 0th is 1. So it's going to tend to e minus 1, which is about 1.728. And that's exactly what we were seeing, because in that sequence of partial sums that we plotted in Desmos, it looked like the y values were tending to something between 1.5 and 2. And that value of e minus 1 is 1.728. So that's pretty spot on. Not bad. Now, I do want to tell you that normally you cannot find what a sequence tends to, or what a series, gosh, I'm going to say that a lot, what a series tends to. In reality, it's very difficult to find out if a series, or not that if a series converges, but that a series converges to a specific value. It's very, very challenging to do that. So most of this chapter is not going to be spent on finding what is the actual sum of the series. Instead, most of the chapter is going to be spent on, can this series, or does this series actually converge to something finite? Because in future math courses, that's going to be critical. You need to know if the series you're working with converges. If it doesn't, you're done with the problem. There's nothing you can do to work on something that doesn't converge. If it diverges, it's infinite, or at least bounces around or something like that. So this is a very unique example in that, because it's a telescoping series, it collapses down and we can actually find its summation. I'll take a drink of my chai. All right. So let's go ahead and see what I have up next. Takes a moment to load. Okay. My note here. It's often necessary for us to re-index a summation or throw out a few terms. This is something, again, that is in the review videos, but it just bears repeating here. So if you were handed a summation, let me get my big pen out. So if you were handed a summation, and that summation went from, oh, I don't know, let's just say n equals 17 to infinity. Notice I'm not starting out 1. And Avi's asking, are all telescoping series convergent? I don't want to say all of them are. The ones I've seen are. I can imagine that you would have a collapsing telescoping series where the final term doesn't tend to 0 or something finite as time goes on. So I don't want to say that they're all convergent. I'm going to say that that when you're working with them, they can collapse down to just being 2 terms, but those 2 terms might be something like this. Let's just say 1/2 to the actually, let's do this. Might be like 1/2. There's a bunch of stuff in between that cancels each other out, and then maybe minus n or something like that at the end. If that's the case, as n goes to infinity, well, that's going to be negative infinity. So that wouldn't converge. But that might be an example that can't exist. I just haven't put my brain to it. But I'm thinking that you could have telescoping series that do diverge. Just offhand, I'm just thinking that. So in this series right here, notice that I didn't start at n equals 1. That's going to be incredibly common in your next course if you take differential equations next. So you have to learn how to re-index things. So let's say that we were dealing with this. That right there. It takes a moment for my screen to catch up, but there we go. So this is a summation from 17 to infinity of 1/2 to the nth power. That is actually a convergent geometric series, which we'll remind ourselves of in a little bit. However, it's most people deal with geometric series starting at n equals 1. You don't have to. The fact that you have some sequence of points that look like this, let's just say. If I want to ignore the first few values of that sequence and just throw them out, so I'm going to just say, let's go ahead and throw these out. Okay. The reality is throwing out a finite number of terms in a sequence or a sequence of partial sums does not change the convergence or divergence, the end behavior. The convergence or divergence of a sequence is all about the end behavior. So you would zoom in here to what happens as n goes to infinity. We don't care about those first few terms. So if somebody said, wait a second, I know if this started at 1 and went to infinity, or better yet, if this started at 0 and went to infinity, I know what it converges to. I know that it converges. Yeah, you're right. It does converge if you started at 0, but we didn't. We threw out the first 17 terms of this, and we're starting at n equals 17. And so because of that, we threw out a finite number of objects, but still in the long run, what matters is not those first 17 terms, but what are the last infinite number of terms? And do those terms tend to something finite? If they do, then we're good, right? And that's the point, is that with series, and I'm kind of addressing the second statement here, but with series, you can always throw out a few terms. That's totally okay. Same thing, and by the way, you could throw out a few terms and it does not affect the convergence or divergence. So neither action affects the convergence or divergence of the series. If I threw out first 1,000 terms, if the series was convergent to begin with, it still is convergent. It's just, yeah, it's just still convergent, right? I've just thrown out a finite number, but if the whole series sums up to be finite, well, then I've subtracted 3 from a finite number. It's still a finite number. If the series ends up tending to infinity and I throw out the first 1,000 terms, and those first 1,000 terms sum up to, let's just pretend 100, well, infinity minus 100 is still infinity. So it's still diverging off to infinity. So throwing out terms does not affect whether a series will converge or diverge. Actually, the same thing for a sequence. Throwing out a certain number of terms is not going to affect the convergence or divergence of a sequence either. And as I said, it's often necessary to reindex a summation. And rather than giving a sub-example, I have actual examples for that. So I'm going to wait and we'll deal with those in a moment. In fact, I think I have that next. So let's go ahead and take a look. Find the first few partial sums. Okay, so the same type of question, right? Find the first few partial sums of this series. Graph the sequence. When I say graph the sequence, I mean graph the sequence. Let me go ahead and write it down. The sequence being a sub n equals n over square root of n squared plus 4. So we're going to graph that sequence, but we're also going to graph the first n partial sums. So maybe the first 100 of them or something like that. And we're going to use Desmos again for that. And then we're going to make a statement. Does it appear to converge or diverge? If it converges, let's try to find its sum. Again, just as that warning, finding the sum of a series is really, really challenging. You need very special series to be able to find their sums. Okay. In this case, notice this series does not start at 1, and that's totally fine. Nobody said it had to. It's totally fine to not start at 1. So let's start at n equals 3. So I'm going to write it this way. I'm going to write, instead of s sub 1, I'm going to call it s sub 3, because honestly, I just want to start at n equals 3 and end at n equals 3. It's a little bit safer to say it that way. So that's going to be 3 over square root of 9 plus, I'll write it that way, 9 plus 4, although we know that's root 13. And then S sub 4. Now, the language that I'm using here, I was saying earlier, S sub 1 is the sum of the first element of our sequence. S sub 2 is the sum of the first two elements of our sequence. Well, if your sequence doesn't start at 1, don't think of it that way. Think of S sub 1 as being the sum of A sub 1, S sub 2 being the sum of A sub 1 plus A sub 2, and so on and so forth. In our case, we start with S sub 3, which should be the sum of A1, A2, A3, but our sequence doesn't start at A1 or A2. It starts only at A3. So this is S sub 3 is just going to equal A sub 3 itself. I should probably write that in. And S sub 4 is just going to be A sub 3 plus A sub 4. Again, because our sequence is not defined to start at 1. So just be careful about that. Not a huge deal. People usually don't have an issue with that. But so we knew that A sub 3 is 3 over root 13. I'm just going to write it that way. Plus A sub 4 is 4 over root 16 plus 4, or root 20. S sub 5, which is A sub 3 plus A sub 4 plus A sub 5, is going to be that 3 over root 13 plus 4 over root 20 plus 5 over root 29. Is that what it is? Yeah, 29. Now, I don't know about you, but this does not, since things are not canceling here, it doesn't look like it's going to be easy to find if this converges, what it converges to. So this, because it's not telescoping, in other words, things don't collapse down and cancel each other out, it's very challenging to see what this would converge to if it converged. But let's go ahead and use now Desmos to graph the sequence and the sequence of partial sums. So I'm going to hop back over to Desmos very quickly. And again, when I found this, I just went to whatever search engine you'd want to go to, and I typed in Desmos sequences. And you're looking for sequences in series, so you could have typed that too. But when I did that, I got, let me close this one. This one doesn't matter. I got this guy right here. Let me go over here. And all I need to do is just change the sequence statement here. The sequence statement right there. I'm going to change to be, I have to go over to my laptop here to find it. Oh, I think I can just remember. I think it was N, and it's capital N, sorry, over the square root of N squared plus 4. Okay, so now remember, in purple is the sequence itself. So this is A sub, we wanted to start at 3, so maybe I should start this at 3. Okay, so we started at 3. So here's the sequence: A sub 3, A sub 4, A sub 5, A sub 6, A sub 7, A sub 8. And actually, when you look at the sequence itself, the sequence is tending to some very beautiful number called 1. And that's what the sequence is tending to. But what about the sequence of partial sums? Well, remember, A sub 3 is always S sub 3. Okay. In fact, let me change this here. It should go from K equals 3 to N. There we go. A sub, interesting, though, it's going to sort of be incorrect. Let me put this as K minus 2. There we go. All right. So this one is S sub 3, which is A sub 3. This right here is S sub 4, which is A sub 3 plus A sub 4. Next one in line is S sub 5, which is A sub 3 plus A sub 4 plus A sub 5, and so on and so forth. You can see that these red dots, which represent the sequence of partial sums, they're just blowing up. They keep rising off to basically infinity. And so this is very, very convincing that this sequence of partial sums that we're seeing in red here, that's going to rise forever and ever and ever. Therefore, the claim that we're going to make is that this sequence diverges, the sequence of partial sums, not the sequence itself, but the sequence of partial sums. So I'll go ahead and state that right here. Let's say, it looks, I'll say it this way, it looks like S sub n, the sequence of partial sums, diverges. And it does, actually. Our goal in this chapter is to find methods to prove that it diverges without having to use technology, because technology can really lie to you when it comes to sequences and series. So we want to fall back to our theory to be able to determine whether a sequence or a series converges or diverges using theory, not just guesses in technology. All right. So again, the point of that example really was to, again, just be able to use technology and to continue to glue together the concept of a sequence versus the sequence of partial sums. So they're two kind of related but different objects. What do we got next? Oh, this is one of my favorite examples. It's such a good example. If the nth partial sum of a series, which the series is defined to be the summation n equals 1 to infinity of a sub n, if the nth partial sum is minus 1 over n plus 1. So somebody comes in the room and they are kind enough to say, hey, guess what? If s sub n, zoom in here. So that is, if s sub n is equal to summation I equals 1 to n of a sub I. In other words, it's a1 plus a2 plus dot, 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 all the way to an. If that's what s sub n is defined to be, which it is, that's how we always define it, then we are given in this specific problem, not in general, just this problem, that a closed formula for s sub n. Somebody was kind enough to do some pre-work for us. They say, hey, guess what? I've done all this work and I found a pattern for s sub n. It always turns into n minus 1 over n plus 1. N minus 1 over n plus 1. And we giggle in delight because that's awesome, because that saves us a ton of work. Well, what do they want? If they've already given us what the nth partial sum is, what else could they want? Well, they say they need to find that we need to find a sub n. What is the base sequence? Notice they didn't give us the base sequence. This guy right here, they didn't give us that base sequence. All they did is say, hey, if you add up the base sequence to the nth term, it turns into n minus 1 over n plus 1. But they never told us the base sequence. But it turns out if they tell me what the nth partial sum is, I can find the base sequence. And they also want us to find what is the infinite sum of that sequence of partial sums, or what is the sequence of partial sums limit to, is really what they're asking. So our goal, I'll write it here, goal, part A, find a sub n, and part B, find the summation. Do they use n or I? I'm sure they use n. Yeah. N equals 1 to infinity of a sub n. Now, just to let you know, that summation notation right there is the same thing as saying I want to find the limit as n tends to infinity. Maybe I should use a different letter than n, as t tends to infinity, of the summation n equals 1 to t of a sub n. It's sort of like actually improper integrals. When you have an infinite limit, you have to change it to limit notation. It is, in fact, almost identical to an improper integral like that. And we know that this notation right here, the sum of the first t terms of our base sequence is written a little bit more cleanly as S sub t. So we're just trying to find what is the limit as t goes to infinity of S sub t, where S sub t is the sum of the first t terms of our sequence. All right. So those are our two goals. Let's go ahead and talk about finding a sub n. So part A. Notice, and this would be kind of hard for a lot of people to invent unless you've seen this. So it's not something that I expect a lot of people to invent on their own. It is a little bit, once you see it, it's like, oh, I could have totally done that. I get it. But getting around to the invention is a little bit odd. So notice this, that if I were to sum up the first n terms of our sequence, it'd be a1 plus a2 plus ... all the way to an. And everybody nods their head. Of course, that's exactly what it's going to be. And if I were to sum up, let's go ahead and sum up the first n minus first terms. Okay. Well, that would be a sub 1 plus a sub 2. And in fact, let me go ahead and just showcase this here, plus a sub n minus 1 plus a sub n plus ... plus a sub n minus 1. So in the first case, S sub n, I added up the first n terms, a1 through an. In the second case, I said, well, what if we only want to add up the first n minus first terms? Well, that'd be a1 plus a2 all the way to a sub n minus 1. But notice, this tells me that if I take the sum of the first n terms and subtract off the sum of the first n minus 1 terms, then you can imagine I'm subtracting all these values between, right? So I'm subtracting, let's see if my highlighter will work. Oof, that's huge. A1 minus A1, A2 minus A2, all the way down to A sub n minus 1 minus A sub n minus 1. And I'm left with A sub n. That's the novel creation of how do I find what a sub n is if I only know what the sum of the first n terms of the series is? Well, this is how it's done. You just say a sub n is just the difference between s sub n and s sub n minus 1. In other words, if I want to get to a good way to think about this is if you want to sum up the first n terms, you would sum up the first n minus 1 terms and add the next term in line. That's another way you can think about that. So that being said, since they handed me a closed formula for S sub n, which is just n minus 1 over n plus 1, that's how I'm going to find a sub n. So a sub n is S sub n minus S sub n minus 1, but S sub n, we've just said, is n minus 1 over n plus 1 minus, and then S sub n minus 1, the sum of the first n minus first terms. Well, that'll be the same structure as this, but instead of n's, you have n minus 1s. I'll write it that way. N minus 1 over n minus 1 plus 1. And we can simplify this if you wanted to. We have all of our mathematics to do that. Minus, what do we have? N minus 2 numerator and denominator. Combine like terms. N times n minus 1 minus n minus 2 times n plus 1 all over n times n plus 1. And you can combine things up. That'd be an n squared minus an n squared in the numerator. Minus 2n plus 1, so it's a minus n plus n. Oh, the n's even cancel. That's kind of nice. And so you get down to negative 2 over n times n plus 1. Check my mathematics there, but I think that's right. So that's what a sub n is defined to be, 2 over n times n plus 1. Kind of nice. It's not too terrible. So that's the trick when you're given the formula for the nth partial sum and asked to find a sub n. Well, just take the nth partial sum, subtract off the n minus first partial sum. That is a sub n. So this formula right here, very, very powerful. I don't want to say it gets used a lot. I don't want to give you the illusion that that's true. It's not. But when you need it, you need it. All right. The second part of this, they ask find the infinite sum, the infinite series. Add the terms up forever and ever and ever. And I spent the time to say, well, that's the same thing as a limit as t goes to infinity of the sum from 1 to t of a sub n, which is just the limit as t goes to infinity of the tth partial sum. So we are going to go ahead and do that. So part B, we want to know the summation n equals 1 to infinity of a sub n. We've already said that's just going to be the limit as t goes to infinity of s sub t, and s sub t is t minus 1 over t plus 1. And we happen to know from our Calc 1, that's going to be 1. That limit will be 1. So here's a really interesting series. They start with not telling us what the base sequence is, but we can find it. And we happen to know that this infinite summation right here, that will converge to 1. Mainly because as n goes to infinity here, that limit will be 1. Notice I'm really taking my time with this because finding that strong distinction between a sequence and its subsequent series is very, very important. So the more time I spend on this, the better it is for you. All right. If you do have questions, please ask. Actually, I'm going to take another sip here. All right, I'm back. Let's see what we have coming up next. Okay, this is a next subsection of this section 11.2. I broke it into like 4 different subsections just so that it's easier to digest and understand. So this subsection is just a review of properties of series. These are from your pre-calc class, but it's still important to mention these. So let's talk about them each individually. If you're given 2 series, and if you see this notation right here where you have a summation of a sub n, and I didn't say n goes from 1 to infinity, that notation is just assuming, let me go ahead and use a different pen actually. So this notation right here is basically the same as the summation n equals some number a to infinity of a sub, oops, I don't want to use a, n equals some number k to infinity of a sub n. So when you see this notation without indices, it's sort of like an indefinite integral where somebody didn't tell you the limits of integration, but the idea is that you're prepping to say that it's going on to infinity. Not that you're doing that with actual indefinite integrals, but whatever. The idea is there. So this just means the infinite sum, a sub n. It could start at 1, it could start at 27, who knows? So if we happen to know the infinite sums, the summation a sub n and summation b sub n are convergent. So those series converge. So we know that if you add the terms up forever, they tend to something finite. That's the idea. So if you happen to be able to add up those terms in a sub n forever and ever and ever, and it becomes 17, and you add up the terms in b sub n forever and ever and ever, and it becomes, let's say, a half, then the following statements are true. The summation of a constant times a sub n is also convergent. Why? because you can factor that constant out. And if the summation a sub n is a convergent number like 17, then and c is a constant, then the answer is whatever that c is times 17. Because each term just has a c in common, you can factor that out. And so that's what this statement right here is. The summation c summation c times a sub n is equal to c times the summation of a sub n. So scalar multiplication is what we'd call that. Scalar multiplication does not affect convergence or divergence of a series. You multiply a series by any, oh, there it goes. My phone is now answering me. It's that time of the semester in a Calc 2 class when your phones will start answering. I just put it away. You'll still answer in that drawer, by the way. So anyway, so this is just something to note for future reference that you multiply a convergent series by any number you want, it's still convergent. You multiply a divergent series by any number you want other than 0, and it's still divergent. If you multiply by 0, by the way, it will converge to 0. It should make sense. Okay. The other one right here, number 2, the summation from k to infinity of a sub I plus or minus the summation from k to infinity of b sub I. And I just chose k because I want to keep it arbitrary. That is also convergent, assuming that the two base series are convergent. So if the base series a sub n, summation a sub n converges, and the summation b sub n converges, then basically adding or subtracting those series will also result in a convergent series. And that convergent series will be this right here. So how we would say this in language is we'd say the sum of convergent series is the series of the sum. Well, it's kind of weird, so I don't want to say that, but that is exactly what's happening, is that you can glue together two convergent series to compute if you wanted to. It's not very common that you would, but you could do that if you want to. And I say proof here. I don't know if I actually want to do a proof on this. Maybe. I might do a proof in a bit. I'm going to go ahead and just spend a moment talking about these notes before I make my decision. So let's see. Note, it is possible. Here's kind of a weirdness with infinite series and calculus, is that it is possible that a sub n, the summation, diverges, and the summation b sub n diverges. It's very possible that both those diverge, but the sum converges. That is, it is possible that that these two series diverge, but this converges. That does happen every once in a while. It's not actually unique. It's just kind of an interesting result. But yeah, it's not like super unique or anything like that. So that's not a biggie, but it is kind of interesting. And then warning, there is no property stating that if you add up a product, that's the same as taking the product of the sums. That is not true. It's totally not true. And in fact, so not true, I'm going to go ahead and spend a moment to give you an example, because this is just super, super duper important. So imagine on my screen, on my desktop, I can't see what I'm doing. Imagine that you have, let's say a sub n. Zoom in here. Let's suppose a sub n is, I don't care, it doesn't actually matter, 1 plus x squared plus ... all the way to x to the nth. I'm using a polynomial. So what else? It's not that big of a deal. Actually, I should say the summation of a sub n is that. Okay. And the summation of b sub n, let's just make that 1 plus y squared plus ... all the way to y to the nth. So what I'm really saying here is that a sub n itself as a sequence is x to the nth power, and b sub n as a sequence is y to the nth power. You double check it. When n is 1 here. We're going to start actually at 0. No, we'll put n minus 1 powers here. And I'll end it at n minus 1. There we go. That's more realistic. When if we say the series is starting at 1, okay, then a sub 1 is x to the 1 minus 1, or x to the 0th, which is 1. A sub 2 is x to the 2 minus 1, which is x to the 1st. A sub 3 is x to the 3 minus 1, which is x to the 7th, and so on and so forth. That's why I'm saying this. Now notice a sub n times b sub n. Let me go zoom out here to make sure that I'm writing this down. Yeah. A sub n times b sub n, and summing it up. Well, if you did that, starting at 1, that'd be 1 times 1 plus. Now going to 2, that would be x times y plus. Now going to 3, that'd be x squared times y squared plus dot, dot, dot. Now think about this. What if it was a sum from 1 to infinity of a sub n times the sum from 1 to infinity of b sub n? Well, let's see. The summation of a sub n, well, that's going to be 1 plus x squared plus dot, dot, dot. The summation of b sub n is 1 plus y squared plus dot, dot, dot. Notice the difference. This you would have to distribute. 1 goes to 1, goes to y squared, goes to dot, 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 right? X goes to 1, goes to y squared, goes to dot, 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 x squared, so on and so forth. Notice in the second summation, we would get terms like xy, which we have here, but we'd also get a term of, I'm trying to find a good one here. Let me go ahead and use this pen. 1 times y. Oh, geez, terrible pen. Let me use a different pen. We get this term 1 times y, yet I don't have a 1 times y in this summation up here. You will never get a 1 times y in that summation. So because distribution comes into play, these two series are not the same. The summation a n b n versus the summation a n times the summation b n. Those are not the same. And so that's what I'm saying here. There's no property that tells us, oh, the sum of products is the product of sums. There's no such property. Okay. So the only properties you can play with for right now are these two properties right here, that if there's a constant multiple, you can factor it out. And if you have two series that are adding up, you can glue them together. That's it. But and adding or subtracting up, I should say. But multiplication, division, there's no theorems for that. We cannot do anything with those. That's usually pretty heavy. A lot of people have a hard time with that. But luckily, you don't see a product of series. Well, okay, that's not true. You do see it in differential equations. At that point, you should never say, oh, yeah, product of series. It's the same thing as a series of their products. That's actually not true. You do not want to do that. It would be terrible. Just take a simple example like, I don't know. Yeah, take a simple example like this. Y versus, let me get a better pen. Take a polynomial example. F of x versus g of x, right? If you were to say f of x is 2 minus x plus x squared, and g of x is, I don't care, 1 plus x plus 2x squared, right? You could see that summing up these values and multiplying it by the sum of these values, well, that would be f times g. That's what f times g is. Oops, it's f of g. So that would be 2 minus x plus x squared times 1 plus x plus 2x squared. That's what this would be. And that would be a big distribution process. Versus multiplying their common terms. So this would be like this. 2 times 1 plus a negative x times x plus x squared times 2x squared. Notice that is much simpler, but totally wrong. These are not the same statements. Totally not the same statements. So just a heads up. It doesn't happen that often, so it's not a big deal. If you stare at this and you're like, oh my God, what did you just say? It, like I said, it doesn't happen enough to be a big deal. Okay. And rather than belaboring that issue and going through a proof, these are actually proved. Aren't they proved in pre-cal? I don't think they are proved in pre-cal. I mean, a really quick proof of the first one, if you want to, you could say, suppose the summation a sub n is convergent, right? Then summation a sub n is equal to s. S is finite, which implies when you multiply both sides by a constant, it's still finite. And that implies, now remember, maybe I should actually write it out. This is a1 plus a2 plus a3 plus dot, dot, dot. You can distribute that C in. And then that summation on the left-hand side can be rewritten as the summation C a sub n. So the summation C a sub n is equal to a constant times a finite number, which is finite. Thus, summation C a sub n is convergent. There you go. So that's a quick proof of the first one. Yeah. I mean, I didn't really prep it, so I just kind of ran through it. But all right, let's see what else we have in store. Oh yeah, this is a good one. Okay, so this guy right here is one of the more important theorems that you're going to run into, and this one we're actually going to prove. This is the birthplace of probably the most important theorem that you're going to have, at least for the first chunk of chapter 11. So if you have a convergent series, so you know that if you add a bunch of terms going on forever and they just become finite, okay, then it must be the case that the sequence tends to 0. Again, if you're adding a bunch of sequence terms together to create a series, and if that summation is convergent, well, then it has to be the case that those sequence terms have to eventually tend to 0. Because if they don't, think about it logically. If your sequence terms do not tend to 0, let me just show this with some dots. Let's suppose that you have these sequence terms. Here's the x-axis. And let's suppose that in the long run, they don't tend to 0. Okay. If that's the case, then remember what you're doing when you're adding up those terms. You're basically saying, I have to use a intelligent color here. I have this value plus 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 this value. And when I get down to this point, I'm thinking, wow, that's great, because the values I'm adding are getting smaller and smaller. So cool. Hopefully they continue to get smaller and smaller, so I add less and less as time goes on. But then if it doesn't end up tending to 0, then you're not adding less and less as time goes on. And that means that the area underneath this curve will grow to infinity. And that marries together our topics, our improper integrals from chapter 7.8, is that if that area underneath that curve does not tend to 0 as time goes on, there's no way the area will become finite. It'll blow up. Same thing here, same idea. All right. A little bit of a warning before we go into the proof. Probably the biggest mistake made is thinking the converse of this theorem is true. That is, people think that as long as the limit as n goes to infinity of a sub n goes to 0, that must imply that our series converges. But that is just not true. Not true at all. So again, as a very important warning, just so important, I just want to say it again. So again, the limit as n goes to infinity of a sub n being 0 says nothing about the convergence or divergence. I'll just say about the summation a sub n. It says nothing about the convergence or divergence of the series. However, if the series converges, that says the sequence has to tend to 0. But just because the sequence tends to 0 doesn't mean the series will. And we actually saw an example like this sort of in 7.8 when we took the integral from 1 to infinity of 1 over x dx. I hope you would agree that this function tends to 0 as x goes to infinity. Totally does. However, the area underneath this curve diverges. And that's by the power series test, or the power test, actually. So it diverges because the power on that x in the denominator is less than or equal to 1. And so I happen to know that area is going to be infinite. Even though the function itself, the 1 over x, tends to 0. So just tending to 0, the argument of the summation tending to 0 means nothing. So that's a heads up. So let's go ahead and prove this theorem here, which is that if our series converges, then it has to be the case that our limit of our sequence tends to 0. Let's go ahead and do that proof. It's important enough to fiddle with. So proof. All right, what can we assume? Well, we can assume that our series converges. That's the only thing you can assume here. So let's go ahead and write that down. Assume that the summation a sub n is convergent. Now, for the purposes of this proof, it's going to be very helpful to go ahead and label that. So we're going to say, what's a good word for that? Specifically, there we go. Maybe I shouldn't say let. We'll just say suppose. No, I guess let. Let S equal the summation. And I'll go ahead and just say I equals 1 to infinity of S sub or A sub I. Come on, erase. So I'm assuming the series converges. And so I'm, in this case, just to some value S. Okay. That's the sum of the series. All right. But let's also go ahead and talk about the nth partial sum. It's my cat. She just likes to meow. It's her favorite thing. So we're also going to just say, well, if I only want to sum up the first n terms, I'll call that S sub n. These are definitional, so not a big deal. All right. I hope that's not a big deal. Well, because we're assuming that our series is convergent, then it must be the case that the limit as n goes to infinity of our partial sums has to be S. I'll say S right here. And by the way, this is the limit. I just want to write this in here. As n goes to infinity of the summation I equals 1 to n of a sub I. So again, these all say the same thing. If I tell you that a series converges, that tells us that the series becomes something finite. And if we say, well, the nth partial sum is just the sum of the first n terms, and we know the series converges, then the limit as n goes to infinity of our nth partial sums must equal that convergent value of s. That's all. Nothing big. But note, the limit, this is going to be a little bit of a trick in here. The limit as n goes to infinity of s sub n minus 1. This is still the nth part, technically the n minus first partial sum. But as n goes to infinity, I hope you would agree that that is still going to be s. No matter what, if n is going to infinity, I add up the first n terms, n is going to infinity, versus adding up the first n minus 1 terms, which n is going to infinity. The reality is it's still n or n minus 1. They're still going to infinity. You're still summing up the first chunk of terms, infinite number of terms of your base sequence. So therefore, in both cases, they should converge both to s. And by the way, this is just to let you know. I'm going to write it this way. The limit as n goes to infinity of the summation I equals 1 to n minus 1 of a sub I. That's just me just filling in for that. And recall from our previous conversation on the other page that s sub n is equal to s sub n minus 1 plus a sub n. In other words, if I want to add up the first 20 terms of our sequence, I could add up the first 19 of them and then add the 20th. But if that's the case, that implies s sub n minus s sub n minus 1 must equal a sub n. Well, this implies, and I see that I'm at the bottom of my page, so I'm just going to go over to the right here. This implies that the limit as n goes to infinity of s sub n minus s sub n minus 1 must equal the limit as n goes to infinity of a sub n. But we've just stated that the limit as n goes to infinity of s sub n getting my handwriting caught up to my language. We've just stated the limit as n goes to infinity of s sub n. That's just s. And the limit as n goes to infinity of s sub n minus 1, well, that's just s as well. And thus, with only the assumption that our series converges, we have shown that the limit as n goes to infinity of our sequence must be 0. And that's only assuming that our series converge. There we go. So that's the proof. If your series converges, then the base sequence must tend to 0 as the end all be all. Now, got to let you know, there is actually a very important side result. I started this page by saying, okay, this is an important theorem, very important theorem, blah, blah, blah. But the reality is you're not going to use this theorem the way that it's written. I'm going to modify the language, but really, before we get there, we have to talk about theorems in general. There's a little thing I want to mention about theorems. And I guess I'm going to do this first. So, example, let's suppose that we have a convergent series. Now, right then and there, I can immediately say if the summation a sub n converges, that should therefore imply by our previous theorem that the limit as n goes to infinity of a sub n must be 0. That's by that previous theorem. Now let's see what we want to do. What can we say about the limit as n goes to infinity of cosine of n times a sub n. Well, I know the limit as n goes to infinity of a sub n is 0. But if you say, well, 0 times anything is 0, you're wrong. In calculus, this is something approaching 0. It's not 0. And so therefore, you cannot say this is 0 times cosine of n, and so it's 0. You have to actually use some theory and rigor. So notice this part right here, the cosine of n as n goes to infinity, that limit does not exist because it's popping back and forth between a bunch of different numbers. So that's the issue, the problem child in this limit. So what we would like to do is bound that. So I'm going to go ahead and trade n's out for x's. Okay. Actually, I'll keep it as n's. That's totally fine. It's not that big of a deal. We happen to know that the cosine of n is always, no matter what, between -1 and 1. Now, if you multiply all three sides of this by a sub n, and by the way, I'm making one slight hand-wavy assumption when I do this. I'm assuming that a sub n is positive. It's not that big of a deal, but just letting you know that I'm just assuming that. So if you multiply both sides, all three sides, sorry, by a sub n, you can see that you have the limit, or you don't have, but we're going to take the limit as n goes to infinity of plus or minus a sub n. The reason why I'm doing that is I want to squeeze the center to something. And notice we have already said, since a sub n is convergent, the summation, sorry, then the limit of the sequence will be 0. Well, because of that, the limit of plus or minus a sub n should be 0. Thus, the limit of what's between negative and positive a sub n, which is a sub n cosine of n, that must be 0. Not because a sub n is tending to 0, but because of the squeeze theorem. There we go. So that's how you would do a problem like that. It's a very nice problem. Just remember from Calc 1 that when you're taking limits of products and one of your factors in that limit does not exist, that limit does not exist, then you're going to have to use something other than just saying 0 times anything is 0. That's not true. You have to use like a squeeze theorem in this case. Now we have 8 minutes, and I think that's long enough for me to mention something here. Yeah. Good way to end the day. Yeah. The divergence test is the next subsection of section 11.2. And it also allows us to talk about every theorem you've ever learned in the past in a single kind of fell swoop. So every theorem you've learned so far in mathematics is actually two theorems in one: the base theorem and its contrapositive. If you don't know that language, I don't blame you. So let's talk about the base, what I mean by a base theorem. A base theorem is an if-then statement. If P is true, then Q is true. That's how most theorems are written. And so a theorem, if it's raining, then it must be cloudy. There's a theorem. I'm just not mathy. It's just a theorem. If it's raining, it must be cloudy. It's a very famous one that's used for this conversation. All right. So that's a base theorem. The contrapositive is the following. Again, if the base theorem holds, then the contrapositive has to hold. And here's the contrapositive. If Q is not true, then P is not true. Every theorem that you've ever encountered in mathematics is actually two theorems. It's the first one that they told you, and the second one, which is the contrapositive. So let's go back to the raining cloudy thing. The base theorem is if it's raining, then it must be cloudy. That should make sense. Its contrapositive is if it's not cloudy, then it's not raining. Again, makes sense. I know you can always create counters to that, but whatever. So that's the contrapositive, is taking the negation of the consequent and saying that implies the negation of the antecedent, is what we'd say. So let's apply that contrapositive thinking to the theorem that we just proved. So our base theorem we just proved was if the summation a sub n converges, then the limit as n goes to infinity of a sub n must equal 0. The contrapositive, which is also true, is the following. If the limit of the base sequence is not 0, then the series a sub n does not converge. That is, it diverges. This is the version of that theorem you're going to use. If you want to determine whether a series is convergent or divergent, this is the first thing you're going to grab. It's called the divergence test. It's the contrapositive of the theorem we just proved. Again, I want to drive home the point that every theorem you're handed, unless it's a bijection, which is an if and only if, but every theorem you've been handed, it has a contrapositive statement that's also true. So for an example, let's see if I can make one out of the Pythagorean theorem. If you have a triangle, or if you have a right triangle with side lengths AB and hypotenuse C, then a squared plus b squared is equal to c squared. Contrapositive. The supposition is that you have a right triangle, or you have side lengths ABC. If a squared plus b squared is not equal to c squared, then you do not have a right triangle. Right? So that's kind of the idea of a contrapositive. Really a cool idea. And again, I want to just forward here to the divergence test in its glorious form. We just actually proved it by proving the basic theorem, the base theorem. Once you prove the base theorem, the contrapositive is always true. So proving the base theorem proves this. So here's the divergence test in all of its glory. It's very fast to use. So I will give you one example as our final example for today. Let me see if I can find one that's fast. Yep. Remember we had this one earlier, and we were asked to write out the first few terms of the summation, and then we used a graph to then say, oh, this looks like it diverges. Well, guess what? It does diverge. Let's go ahead and prove it. We'll take the limit of the base sequence that this series is based upon. The limit as n goes to infinity of n over the square root of n squared plus 4. Dividing both numerator and denominator by n, you get this, the limit as n goes to infinity of 1 over the square root of, when I divide this by n, it becomes an n squared on the inside, so it'll be a 1 plus 4 over n squared. As n goes to infinity, we happen to know this guy right here will tend to 0. And so this tends to be 1, which is definitely non-zero. So as n goes to infinity, the sequence that the series is based upon is not 0. Thus, the series diverges. Summation n over root n squared plus 4 diverges. And you will always cite the divergence test. So by divergence test. And when you write by the divergence test, you can actually shorten that up to dt. Divergence test is super powerful because, again, as we move forward in this chapter, we're going to be asking over and over again, does this series converge? Does it diverge? Your first knee-jerk reaction should be, let me see if the sequence tends to something other than zero. Because if it does tend to something other than zero, then I know the series diverges immediately by the divergence test. All right. That's a good stopping point. I know it's very dense material. Welcome. Chapter 11 is full of dense material. I'll be back in 10 minutes. I will also be continue grading the exams. I'm about 2/3 of the way through, but not completely done. So I should finish sometime today. All right. You guys have a wonderful day. And I will see you in office hours if you're going to be there in 10 minutes. Take care.